Welcome to G Fun Facts Online. Beneath the desolate, howling surface of the Antarctic and Greenland ice sheets lies a hidden, alien world. We are talking about a submerged landscape of deep canyons, towering subglacial mountains, and sweeping plains. For over a century, scientists looking to predict the future of global sea levels focused primarily on the sky. They measured air temperatures, tracked atmospheric greenhouse gases, and built climate models based on what was happening above the ice. But over the last few decades, a quiet, almost terrifying revolution has taken place in the field of glaciology. We now know that the ultimate fate of our coastlines is not just written in the warming air above us, but it is etched into the very shape of the bedrock buried miles beneath the ice. This realization hinges on a profound geophysical concept called Marine Ice Sheet Instability, or MISI for short. It is a mechanism of runaway, self-sustaining ice loss, driven by the interplay between warming oceans and the hidden topographical slopes of the continent. Alongside its highly debated cousin, Marine Ice Cliff Instability, MISI represents one of the most critical tipping points in the entire Earth climate system. To truly understand why glaciers the size of Great Britain are teetering on the edge of total collapse, we have to take a journey to the grounding line. This is the dark, highly pressurized frontier, where ice, ocean, and bedrock collide. Let us start by understanding the anatomy of a marine ice sheet, because not all ice sheets are created equal. A terrestrial ice sheet, like the vast majority of East Antarctica, rests on bedrock that is situated above sea level. If these glaciers melt, they do so largely from the top down, driven by warming air temperatures in the atmosphere. A marine ice sheet, however, is a completely different beast. Vast swaths of the West Antarctic ice sheet rest on bedrock that is plunged hundreds, and in some places thousands, of meters below sea level. The ice here is so unimaginably thick, often spanning over a mile deep, that its sheer weight literally displaces the ocean water, allowing the ice to sit firmly on the submerged ocean floor. The architecture of a marine ice sheet can be divided into three distinct zones. First, we have the grounded ice. This is the colossal interior mass of the ice sheet that rests directly on the continental bedrock. Second is the ice shelf. As the immense weight of the ice slowly flows outward from the center of the continent toward the coast, it eventually detaches from the sea floor and begins to float. This floating extension is the ice shelf, and it plays a vital mechanical role. Ice shelves act like structural buttresses, or if you prefer a simpler analogy, they act exactly like corks in a champagne bottle. They provide intense physical resistance, pushing back against the immense weight of the grounded ice behind them, slowing its march into the sea. And finally, the third zone is the grounding line. This is the pivotal boundary, where the ice detaches from the bedrock and begins to float. It is the transition zone between the grounded ice and the ice shelf. The grounding line is arguably the most important battleground in global climate science today. It is not a static marker drawn on a map, it is highly dynamic. If the ice shelf thins or melts due to warming ocean currents, it loses its buttressing power. The grounding line is then forced to retreat inland. But whether that retreat is a slow, gradual crawl or a catastrophic, unstoppable collapse depends almost entirely on the shape of the bedrock below it. To comprehend the nightmare of marine ice sheet instability, we have to look at the geological canvas upon which it plays out. The stability of a grounding line is governed by the slope of the subglacial topography. Let us break this down into two types of slopes, prograde and retrograde. First, let us look at prograde slopes, which are stabilizing. Imagine a beach that gently slopes upward as you walk inland away from the water. This is a prograde slope. If an ice sheet is resting on a prograde slope, a warming ocean might melt the front of the ice, causing the grounding line to retreat slightly inland. However, as it retreats, it moves onto shallower, higher ground. Because the ice at the new grounding line is in shallower water, the cross-section of ice exposed to the ocean is smaller. The ice flow naturally slows down, and the system easily establishes a new, stable equilibrium. Prograde slopes essentially act as natural brakes for glaciers, but then we have retrograde slopes, which are inherently destabilizing. Now, I want you to imagine a landscape that behaves like a deep bowl. As you move inland from the coast, the bedrock does not rise. It dips deeper and deeper below sea level. This is a retrograde slope or a reverse bed gradient. Much of West Antarctica, which has been pressed down over millions of years by the unimaginable weight of the ice, is shaped exactly like this deep bowl. When a grounding line is forced to retreat down a retrograde slope, a nightmare scenario in glaciological physics is triggered. Here is exactly how this chain reaction works. Step 1. As the warming ocean melts the ice shelf, the grounding line moves inland, sliding down the slope into deeper water. Step 2. Because the water is deeper, a taller, thicker column of ice is suddenly forced to float. Step 3. According to the fundamental laws of glaciological physics, the amount of ice flowing across the grounding line, known as the ice flux, is highly sensitive to the thickness of the ice at that exact point. To put it simply, thicker ice flows much faster than thinner ice. Step 4. Because the retreat has exposed thicker ice to the ocean, the glacier speeds up, dumping even more ice into the sea. Step 5. This rapid acceleration stretches and thins the grounded ice just behind the line, causing it to lose its grip and lift off the bedrock. This forces the grounding line even further inland, into even deeper water, exposing even thicker ice. This is the essence of marine ice sheet instability. It is a self-sustaining, positive feedback loop. Once the grounding line retreats past a certain high point, like a subglacial ridge, and begins slipping down a retrograde slope, the process becomes virtually irreversible. Even if ocean temperatures were to miraculously cool back down to pre-industrial levels tomorrow, the pure physics of the deepening bedrock would ensure that the glacier continues to hemorrhage ice into the sea until it finds a new shallow ridge, which might be hundreds of miles inland. In fact, a 2019 mathematical analysis using a complex framework called stochastic perturbation theory demonstrated that MISI drastically amplifies the uncertainty in our global sea level projections, heavily skewing all outcomes toward worst-case scenarios. The reverse-sloping bedrock essentially turns gradual climate warming into a non-linear planetary emergency. There is no place on Earth where the threat of MISI is more immediate or consequential than the Thwaites Glacier, located in the Amundsen Sea sector of West Antarctica. Roughly the size of Great Britain or the U.S. state of Florida, Thwaites is a colossal river of ice currently losing approximately 50 billion metric tons of mass every single year. Let that number sink in. 50 billion metric tons annually. This single glacier accounts for around 4% of all global sea level rise right now. If Thwaites were to melt completely, it would raise global sea levels by roughly 65 centimeters, which is over 2 feet. However, Thwaites is not just a massive glacier. It is considered the keystone holding back the rest of the West Antarctic ice sheet. If Thwaites collapses, it removes the cork from the bottle, which could trigger a regional destabilization, leading to over 3.3 meters, or 11 feet, of sea level rise. That is enough water to drown major coastal cities from Miami to Jakarta. Because of this monumental threat, in the early 2020s, a joint United Kingdom and United States initiative called the International Thwaites Glacier Collaboration deployed fleets of satellites, underwater robots like the torpedo-shaped ice fin, and hot water drills to probe the glacier's deepest vulnerabilities. The discoveries they made between 2023 and 2026 have fundamentally reshaped our entire understanding of glacial demise. First, let us talk about the subglacial trenches and the role of El Niño. Researchers mapping the bedrock topography of Thwaites discovered a massive labyrinth of deep trenches, some up to 800 meters deep, carved right into the seafloor beneath the ice. These channels are not just empty space. They act as superhighways for something called circumpolar deep water. This is a relatively warm, salty ocean current that circles the continent. Shifting wind patterns, which have been exacerbated by climate change and intense El Niño events, have weakened the Pacific trade winds. This weakening allows this warm, deep water to well up onto the continental shelf and penetrate deep into the dark belly of the glacier. But the true shock came in 2024 with the discovery of tidal pumping. For decades, scientists modeled grounding lines as relatively static boundaries. But utilizing high-resolution synthetic aperture radar from the ICEYE satellite constellation, glaciologists made a staggering, almost unbelievable observation. The immense surface of the Thwaites Glacier, resting over 1,000 meters thick, was visibly rising and falling by tens of centimeters twice a day, perfectly in sync with the ocean tides. Eric Rignot, a lead researcher from NASA's Jet Propulsion Laboratory, described the zone where the ice rests on the seafloor as the Achilles heel of the glaciers. The tides were acting like a giant mechanical lung. As the tide rose, it lifted the entire multi-billion-ton glacier, pumping warm, highly pressurized seawater as far as 60 kilometers or 37 miles beneath the grounded ice. This vigorous melting from tidal pumping heavily lubricates the bedrock, degrades the ice from the bottom up, and vastly accelerates the onset of MISI. Because of these hidden pressurized seawater intrusions, the volume of fresh water flowing from Thwaites into the ocean has more than doubled since the 1990s. And the protective ice shelf in front of Thwaites? It is currently shattering. In 2019, the shelf suffered massive cracks, leading to the calving of huge icebergs. By late 2024, comprehensive studies indicated that the structural integrity of the Thwaites ice shelf was in its final stages of failure. A complete disintegration of the floating portion is expected within the decade. Once that buttress is gone, the grounded ice will be fully exposed to the retrograde slope of the bedrock, potentially locking in the MISI feedback loop for centuries to come. As if the mechanism of MISI were not concerning enough, the scientific community has recently wrestled with a secondary, even more violent theoretical mechanism known as Marine Ice Cliff Instability, or MICI. Introduced into prominent climate models by researchers Rob DeCanto and David Pollard in 2016, MICI operates on the absolute limits of materials science. Here is the premise. If an ice shelf collapses completely, it does not just expose a gentle slope of ice to the ocean, it exposes a vertical cliff face. Ice, despite its apparent rigidity and hardness, is actually a quite weak material on a macro scale. The MICI hypothesis posits that an ice cliff towering more than 100 meters above the waterline simply cannot support its own immense weight. The internal stresses at the base of the cliff would vastly exceed the sheer strength of the ice itself, causing the cliff to violently fracture and collapse into the sea. Because the glacier rests on a retrograde slope, as the front cliff face collapses, it exposes an even taller, thicker cliff right behind it. This triggers a runaway, domino-like effect of continuous structural failure, causing the ice sheet to disintegrate at terrifying, unprecedented speeds. The inclusion of MISI in some predictive models was so alarming that it led the Intergovernmental Panel on Climate Change to introduce a low-likelihood, high-impact storyline in its 6th assessment report. This extreme scenario projected that Antarctica alone could contribute twice as much to sea level rise by 2100 than previously expected, and up to a staggering 15 meters by the year 2300. However, the scientific community remains fiercely debated on the true immediacy and mechanics of MICI. Recent high-resolution modeling, including a landmark 2024 study published in the journal Science Advances, led by Dartmouth researchers, suggests that the apocalypse of crumbling ice cliffs might not happen quite as rapidly as once feared. When these researchers implemented advanced physically motivated models that accounted for exactly how ice flows and deforms under extreme pressure, they found a natural stabilizing effect. When an ice shelf collapses, the immense pressure of the grounded ice behind it causes the glacier to surge forward and flow faster. This rapid forward flow actually stretches and physically thins out the ice near the margin. As the ice stretches and thins, the overall height of the terminal cliff drops below that critical 100-meter threshold, effectively stabilizing the cliff face and preventing the rapid, domino-style collapse. Furthermore, Jeremy Basis, a prominent glaciologist from the University of Michigan, ran simulations showing that even as massive ice cliffs shatter and fall, the icy rubble and debris accumulating at the base of the cliff in the water act as a temporary buttress, effectively slowing the rate of failure. So, does this mean the coastal cities of the world are safe? Absolutely not. As the authors of the Dartmouth study emphasized, while the immediate structural collapse driven by MICI might be slower to trigger than the most extreme models suggested, the underlying, unstoppable threat of marine ice sheet instability remains fully active. Thwaites is still retreating, it is still losing mass at an astonishing rate, and the bedrock is still sloping downwards into the abyss. The delay of MICI only buys humanity a narrow window of time, not a pardon. And we must understand that this is not just a West Antarctica problem. while the Amundsen Sea embayment, which hosts Thwaites and the neighboring Pine Island Glacier, is the poster child for MISI. Retrograde topography is a hidden danger globally. Take East Antarctica, for example. For decades, the East Antarctic ice sheet was considered the stable, sleeping giant of the global climate. Holding the vast majority of the world's fresh water, it sits largely on high continental bedrock. However, advanced radar mapping technologies, like the BEDMAP2 database, have revealed that massive sectors of East Antarctica, such as the Wilkes subglacial basin, are actually marine-based and rest on deeply retrograde slopes. If warm ocean currents manage to infiltrate these East Antarctic basins, they could trigger MISI in regions previously thought to be completely invincible. Findings explicitly warn that immediate decarbonization is the only way to prevent the initiation of unstable retreat in the marine-based sectors of East Antarctica. In the Northern Hemisphere, the Greenland ice sheet presents a slightly different topography. It is characterized by deep, narrow fjords rather than broad marine basins. However, many of Greenland's massive outlet glaciers, such as the Jakobshavn Glacier, rest on reverse-sloping beds within these dark fjords. As warm Atlantic water pushes into these fjords, it melts the glaciers from below, forcing rapid retreat. While Greenland's total sea level equivalent is lower than Antarctica's, coming in at roughly 7 meters, its current rate of mass loss is incredibly steep, driven by a combination of extreme surface melting and marine instability at the deep grounding lines. To truly grasp the complexity of this system, we have to look at the physics of water and bedrock, specifically subglacial hydrology. The relationship between ice and bedrock is mediated by an invisible, highly pressurized layer of water. The immense pressure of the ice sheet miles overhead actually lowers the melting point of ice at the base. Combined with geothermal heat rising naturally from the Earth's crust, this creates a vast subglacial hydrological system. We are talking about a dark network of lakes, rivers, and swamps hidden entirely from the sun. This basal water acts as a high-pressure lubricant. Where the bedrock is rough and dry, the ice flow is slow, held back by massive basal friction. But when subglacial water pools on retrograde slopes, the glacier essentially hydroplanes. Furthermore, as the grounding line retreats down a retrograde slope, warm ocean water can spill over high subglacial ridges, carving out vast, echoing cavities beneath the ice. These cavities allow dense ocean water to mix with light, fresh subglacial meltwater, creating turbulent, swirling eddies that further scour the underside of the glacier, rapidly dissolving the ice from the bottom up. With all this catastrophic mechanism at play, is there any natural force that can halt MISI once it starts? There is exactly one geological phenomenon that offers a glimmer of hope, and it is called glacial isostatic adjustment, or simply bedrock rebound. The Earth's crust is not entirely rigid. It floats on the viscous, highly heated mantle below. The monumental weight of an ice sheet pushes the continental bedrock down deep into the mantle. If an ice sheet melts rapidly due to MISI, that immense weight is suddenly removed. Over time, the bedrock will actually bounce back, rising upward. In theory, if the bedrock beneath a retreating grounding line rebounds fast enough, it could shallow the water, shift the topography from a retrograde to a prograde slope, and naturally halt the instability. However, the viscosity of the Earth's mantle varies globally. While some areas of West Antarctica have relatively runny mantles that allow for fast rebound, scientists generally agree that this geological bounceback operates on timescales of centuries to millennia. It is simply far too slow to save modern coastal communities from the rapid inundation expected over the next 100 years. The horrifying, locked-in certainty of bedrock topography has forced some scientists to think far beyond standard emissions reductions and consider active, large-scale planetary intervention. If the ocean is the weapon and the retrograde slope is the vulnerability, can we build a shield? In 2024 and 2025, glaciologists John Moore and Michael Wolovic gained significant global traction for a radical geoengineering proposal, building an artificial barrier on the seafloor to protect the Doomsday Glacier. This concept does not involve building a solid concrete dam, which would be instantly destroyed by the crushing force of mega icebergs. Instead, they propose anchoring a massive, flexible, buoyant sea curtain to the bedrock of the Amundsen Sea. This 100-kilometer-long curtain would rise from the ocean floor, specifically designed to block the deep, warm, circumpolar deep water from flowing into the subglacial trenches beneath Thwaites, while allowing the cold, fresh surface water to flow over the top. By starving the grounding line of its thermal fuel, the sea curtain could theoretically halt the basal melting, allowing the ice shelf to thicken, reground on the seabed, and permanently halt the MISI feedback loop. While the engineering challenges are bordering on the impossible, requiring autonomous operation deep underwater in bone-chilling, iceberg-choked, tempestuous seas, the proponents argue that the cost of such a mega-project, estimated in the tens of billions of dollars, pales in comparison to the tens of trillions of dollars in economic damages that a 3-meter global sea level rise would inflict on global real estate, infrastructure, and agriculture. Still, critics strongly warn that geoengineering the pristine Antarctic is fraught with massive ecological risks, and more importantly, it fundamentally distracts from the absolute root cause of the crisis, the unabated burning of fossil fuels. It is a profound and unsettling paradox that the daily lives of billions of people in the 21st century will be dictated by the shape of submerged rocks that human eyes have never directly seen. The consequences of marine ice sheet instability will absolutely not be contained to the polar circles. A retreat driven by retrograde topography will fundamentally reshape the global map. Current trajectories, amplified by MISI, suggest sea level rise could easily exceed 1 to 1.5 meters by 2100 if these critical tipping points are fully crossed. Cities like Miami, New York, Mumbai, Shanghai, and Dhaka face direct existential threats. Low-lying island nations such as the Maldives and Tuvalu will be wiped from the map entirely. Beyond coastal inundation, the catastrophic influx of hundreds of billions of tons of cold, fresh meltwater into the Southern Ocean severely disrupts the global thermohaline circulation. This alters weather patterns on a global scale, shifting vital rainfall belts, intensifying tropical cyclones, and creating more extreme, unpredictable agricultural seasons that threaten global food security. The slow-motion collapse of global coastlines will trigger an unprecedented migration crisis, as hundreds of millions of people are violently forced inland. The mass abandonment of coastal real estate will lead to systemic financial shocks, as global mortgages literally and financially go underwater. The study of marine ice sheet instability and bedrock topography forces us to deeply confront the non-linear nature of the Earth's climate system. We are so used to thinking of climate change as a simple thermostat. Turn the heat up, things get predictably worse. Turn the heat down, things get predictably better. But MISI teaches us that the Earth does not have a thermostat, it has trapdoors. The retrograde slopes of West Antarctica are a geological trapdoor. We are currently applying the immense thermal pressure of global warming directly to the hinge. Our sophisticated satellite networks, our robotic submarines diving into the dark crevices of Thwaites, and our advanced supercomputer models all confidently tell us the exact same story. The ice is thinning, the ocean is warming, and the grounding line is dangerously slipping down the slope. While the academic debate over the rapid structural collapse of towering ice cliffs may adjust the timeline slightly, the underlying physics of marine ice sheet instability remain an undisputed, looming threat. Immediate, sustained global decarbonization to keep global temperatures within the 1.5 degrees Celsius Paris Agreement limit is the only scientifically sound method we have left to prevent the ice from fully crossing the threshold into irreversible collapse. The subglacial topography is fixed, the bedrock will not move. The only variable left in the equation is us,